Let's dive right in with an interesting problem. What is the value of the number 421 if we assume it's written in base 5? Not so common, right? You might be more accustomed to our usual decimal system, which is base 10, but exploring other bases can be quite exciting. Now, we can write this number with the subscript 5 to indicate that it's in base 5. And how do we convert it to base 10, you ask? Simple. We multiply each digit by 5 raised to the power of its position, counting from 0 for the rightmost digit. So for the number 421 in base 5, we have the rightmost digit, 1, multiplied by 5 to the power of 0, which is 1 times 1, the middle digit, 2, multiplied by 5 to the power of 1, which is 2 times 5, and lastly, the leftmost digit, 4, multiplied by 5 to the power of 2, which is 4 times 25. If we add those up, we get 100 plus 10 plus 1, which equals 111 in our usual decimal system, base 10. Let's keep the ball rolling with another example. Now we have the number 121 in base 4. Yes, we're delving into even less common territory here, and we write it as 121 with subscript 4 to denote that it's in base 4. Just like before, we're going to convert it to base 10. We follow the same rule, multiplying each digit by 4 raised to the power of its position, again counting from 0 from the right. This means, for 121 in base 4, we do the following. The rightmost digit, 1, multiplied by 4 to the power of 0, which gives us 1. The middle digit, 2, multiplied by 4 to the power of 1, which gives us 2 times 4 or 8. And finally, the leftmost digit, 1, multiplied by 4 to the power of 2, which is 1 times 16. Summing these results gives us 16 plus 8 plus 1, which is 25 in decimal notation. So 121 in base 4 equals 25 in base 10. Fascinating, isn't it? We're effectively translating between different numerical languages. Let's hop on our number train to the base 6 station. Our passenger today is the number 234. To convert this to a familiar face in base 10, we multiply and add as we've done before. For the rightmost digit, we have 4 times 6 to the power of 0, which equals 4. In the middle, we have 3 times 6 to the power of 1, which equals 18. And our first class, leftmost digit gives us 2 times 6 to the power of 2, which is 72. What's the total ticket price for this base 6 journey? It's 4 plus 18 plus 72, which equals 94 in base 10. Easy as pie. Next up, we've got the number 321, a classic backward countdown, but in base 7. Let's take this countdown to our comfortable base 10. Starting at the right, we have 1 times 7 to the power of 0, which equals 1. In the middle, we have 2 times 7 to the power of 1, which equals 14. And finally, 3 times 7 to the power of 2 gives us 147. When we add these up, we get 162 in base 10. Who would have thought a countdown in base 7 could lead us here? Last but not least, we're tackling the number 111 in base 9, or as we mathematicians write it, 111 with subscript 9. With all these ones, you'd think we were playing a slot machine. We start on the right with 1 times 9 to the power of 0, which equals 1. The middle digit gives us 1 times 9 to the power of 1, which equals 9. And the leftmost digit results in 1 times 9 to the power of 2, which is 81. Adding these up, our lucky slot machine gives us a total of 91 in base 10. Jackpot! We've successfully navigated from base 9 to base 10 with ease. Here we are at our final destination, a deep dive into the truths that hold for any base. These principles, my dear number navigators, are like the North Star guiding us through the universe of numbering systems. Firstly, the number of digits used in a system equals the base number itself. For instance, base 2, which you might know as binary, only uses 0 and 1. And our comfortable base 10 uses 10 digits, ranging from 0 to 9. Speaking of 0, it's the number system's VIP, appearing in every base as one of the digits. No matter which base you're in, 0 is always there, like a faithful friend. The largest digit in any base is always the base -1. So in base 10, the largest digit is 9. In base 2, it's 1, and so on. Now here's where things get a little abstract. The numeric value of a number, represented by a sequence of digits, is determined by the relative positions of the digits within the sequence. This means that a digit in a higher position has more weight or value than a digit in a lower position, and this weight increases with the base. Finally, here's a fun fact to ponder over. Larger numbers can be represented using fewer digits as the base increases. So in binary, the number 16 would take 5 digits, while in base 10 it's only 2 digits. That's a space saver for sure, especially when dealing with large numbers. So whether you're counting apples or solving a complex equation, remember these principles. They're the heartbeat of all base systems and your key to unlock the secrets of any base.